Hello and welcome to this latest installment in the Black Hat webinar series, Hunting Malicious Machine Learning Models, Insights from Analyzing 1.5 million Nefarious ML Models, sponsored by JFrog and broadcast by Black Hat and Informa. Terry Sweeney here with Black Hat. I'll be your moderator today. Just a few quick logistics before we get started. Some context first, though. In 2024, the number of open source ML models tripled, while ML model attacks increased 6.5 times, which pretty much demonstrates that attackers are just showing how easy it is to gain remote code execution using malicious ML models. This trend, combined with the high number of vulnerabilities and the lack of awareness and effective automated tools with ML modes, leaves users very vulnerable. JFrog's own security research team looked at more than 1.5 million publicly available models, revealing the latest malicious techniques used by attackers, how current security solutions can be bypassed, and the limitations of inherent defenses in ML libraries. So to make more sense of this for us, I'm excited to introduce our speaker today. I'm joined by Ofri Ozan, security researcher at JFrog. Thank you for coming on. But before I hand it over to Ofri officially, I just want to remind our audience of a couple of things. If you've been here before, you know this webinar is designed to be interactive between you and the speaker. At the bottom of your screen, there are buttons you can click on to learn more about our speaker, share this webinar on social media, and this is also where you'll participate in the Q&A session that takes place at the end of the presentation. You can also use that Q&A area to let us know if you're having any technical problems. Our team will do their best to assist you. All right, let's get right to it then. Ofri, the floor is yours.
Thank you for the introduction. Hi, everyone, and welcome to this webinar of Hunting Malicious ML Models, where we're going to share our insights from analyzing 1.5 million nefarious ML models. Before we start, here's a little bit about me. I am Ofri Ozan, a security researcher at the JFrog Security Research team. In my work, I focus on uncovering vulnerabilities and researching exploitation techniques in all fields related to the software supply chain security. I'm passionate about uncovering security issues, presenting them in conferences, and solving them. Today, I'm going to present a webinar, and Shahar Menashe, who is the VP of JFrog Security Research, will answer your questions. Shahar played a significant role researching this topic and building JFrog's capabilities around it. Feel free to type your questions in the chat at any time, or you can ask them at the end during our Q&A session. So, this webinar is all about ML model attacks and the insights we've gained from researching 1.5 million models. So we'll begin with a quick introduction to Hugging Face, the platform we'll be focusing on throughout the session. We'll then dive into the most popular ML libraries and their corresponding model formats, map them to relevant threat types, and share real-world examples of malicious model attacks. Next, we'll explore the different ways to protect against malicious ML models, starting with existing scanners used to detect malicious models, and understand how these can be bypassed. We'll also look at mitigation techniques provided by ML libraries and understand how attackers are able to work around those as well. And of course, we'll also address one of the most critical issues with model scanners, the high rate of false positives. We'll examine why this happens and how it can be mitigated. And throughout the session, you'll gain actionable takeaways on how to protect your environment from malicious models and avoid potential damage. So, why am I here giving this specific session? As always, attackers are quick to exploit new technologies to compromise users and organizations. For years, it's been known that they target third-party packages injecting malicious code that gets downloaded and executed by victim users. Now, with the rapid rise of AI, we're seeing similar trend with machine learning models. popular ML models are being published for external use and downloaded millions of times. You can see a screenshot from Hugging Face of some of the most downloaded models. So attackers started to looking for ways to plant malicious code into ML models, same they did with packages, that as a result will be downloaded and executed when these models are loaded. Before diving into the threats, let's take a moment to understand the Hugging Face ecosystem. Hugging Face is a collaborative platform where the machine learning community shares and builds models, datasets, and applications. The platform supports over 50 different ML tasks, including image-to-text, object detection, mask generation, translation, and more than 50 libraries such as PyTorch, TensorFlow, JAX, Transformers, Safe Tensors, GGUF, ONNX, and others, and models in 4,800 plus languages, including English, French, Chinese, Italian, German, Hebrew, and many more. The JFrog Security Research team continuously scans for malicious models on Hugging Face. In March 2024, there were 500,000 models available with just over 60 identified as malicious. Fast forward to March 2025, that number jumped to 1.4 million models, with more than 340 classified as malicious. This represents a 3x increase in total number of models and nearly 6x increase in malicious models in just 1 year. Let's first understand how ML models are built. Other core machine learning models are mathematical structures trained to perform tasks such as classification, translation, object detection, image generation. Once trained, models can be saved to the disk for reuse, either for inference or for fine-tuning. And most ML models include three main components. The first is weights, which is what I refer to as the knowledge. These are the numerical values the model learns during training. Weights encode what the model knows and are essential to its ability to perform tasks with accuracy. The second is metadata, which is what I refer to as the context. The metadata includes all the descriptive information about the model. What's the goal of the model? For example, is it translation, object generation, what languages it supports, and which library or framework it uses, like PyTorch or TensorFlow. And it also contains details like author, license, and tokenizer settings. And the third is architecture, what I refer to as the brain's wiring. This defines the model structure, the sequences of layers, their types, and how they're connected, and how data flows through them. On paper, most model formats appear similarly. They have weights, metadata, and architecture. But in practice, the way each framework stores this information is very different. And understanding these differences is critical, especially from a security perspective. Let's cover some of the most popular models hosted in Hugging Face. The first and currently most popular format is Safe Tensors, which was developed by Hugging Face to store model weights with over 800,000 downloads. It doesn't store the model architecture, which actually makes it safer against code execution attacks. Then there's PyTorch with over 200,000 downloads, which was originally developed by Facebook. Now it is maintained by Meta AI. PyTorch models are typically saved using Python's pickle mechanism, which we will cover later in the presentation. PyTorch can be saved either with just the weights or with both the weights and architecture. GGUF is next with over 100,000 downloads. It's a newer format developed by the JGML community, designed for efficiency loading large language models in an environment like Llama and Ollama. ONNX, which became popular recently with over 20,000 downloads, It stands for Open Neural Network Exchange, a format that was initially developed by Microsoft and Facebook and meant to support cross-framework model sharing. And lastly, TensorFlow, which although widely used in the industry, has just over 14,000 downloads on Hugging Face. It is developed and maintained by Google, supports models format like Saved Model, Keras, and HFAV. Now let's take a closer look at PyTorch, one of the most widely used Python libraries for training machine learning models. After training a model in PyTorch, there are two main ways you can save it. The first approach is to save only the learned weights using torch save. This saves just the parameters using the state ticked, not the model structure, so the user has to manually rebuild the model architecture in code before loading the weights. And the second approach is to save both the model architecture and the weights using the PyTorch default torch save function. And here is the important part. PyTorch standard saving format is based on Python's pickle module, and that's where things can get risky. So let's get familiar with pickle, as this is a key concept. Pickle is a Python module used for serializing and deserializing Python objects. However, as clearly stated in the official documentation, Pickle is considered unsafe when loading data from untrusted sources because it allows arbitrary code execution. For that reason, it's strongly recommended to not unpickle data from sources you fully trust. The core issue lies in the fact that Pickle doesn't just store the object's data. It can also store instructions for how to reconstruct the object, including function calls. So when loading a Pickle file using pickle load, Python checks whether the object being reconstructed implements one of the three special methods: reduce, reducex, and setState. The purpose of reduce is to define how to reconstruct an object during unpickling. It returns a tuple where the first element is a callable. This can be a function or a class. The second element is a tuple of arguments to pass to that callable. During deserialization, Python calls the callable with the given arguments. For example, if the callable is OS system and the argument is echo exploited, it will execute that system command as soon as pickle is loaded. ReduceX is nearly identical to reduce, but it receives an additional protocol version argument. Python prefers calling reducex over reduce if both are defined. So that's why attackers prefer targeting reducex for exploitation. Same as reduced, Python calls the callable with the given arguments. The setState method works a bit differently. Its purpose is to restore the object's internal state, typically from a dictionary or other serializable data. Instead of returning a callable, setState is automatically invoked after the object is created. But because arbitrary code can be placed inside this method, it becomes another opportunity for malicious code execution. For example, if OS system echo exploited is placed inside setState, it will run as soon as unpickling finishes constructing the object. As mentioned earlier, PyTorch standard model saving format is based on Python's pickle module. One of the most well-known model threats targeting this format is what we define as PyTorch malcode, which leverages the same pickle-based exploitation techniques we just explored. The torch load function internally uses pkload, which means when used, it invokes code from the three methods we explored: reduce, reducex, and setState. Usually the code inside these methods, what we call setup code, is supposed to set environment variables, optimize performance based on the local system, or download additional dependencies. In ML models, it is extremely rare that ML model authors would choose to inject the legitimate model setup code into the model's pickle data. This setup code is what makes it possible for malicious actors to execute arbitrary code, as they can create a model, write an arbitrary code, which is the setup code, inside one of the three methods that is serialized and deserialized via pickle, that as a result will be executed when the model is loaded. And all of that happens before the model is used for any predictions or inference. In case setup code is needed to be used legitimately, a safe use of that should be bundling it outside of the pickle data, either manually by the model's user that reads the model's usage guide, or automatically by the library that loads the model. Now, to safely determine if the suspected model contains malicious pickled code, you should first extract the suspicious PyTorch model as a zip archive to retrieve the data pickle file. Then decompile the data pickle file using some tools, for example, pickling. And finally, examine the decompiled Python code to determine if it contains any malicious instructions. Here you can see a simple example of extracting an ML model using the pickling tool. Another well-known model threat targeting the pickle format is what we define as PyTorch getATR. This model threat relies on PyTorch with pickles as we just explored, but this one can evade some scanning techniques. Let's first understand what getATR is. So getATR is a built-in Python function that can dynamically access attributes or methods of an object by name using a string. It is a legitimate and useful function to dynamically access methods or properties by providing their name. However, the risk is that getATR can be used to execute code. For example, attackers can use the getATR function with OS and provide system as a parameter, which opens a shell for executing malicious commands, such as the destructive shell example you can see here. The special thing is that it is done in a stealthy way, because this technique can avoid obvious function calls that scanners look for, such as OS system, subprocess, etc., by hiding them in getATR. In order to not miss these cases, scanners need to monitor getATR calls. However, alerting on any call of getATR significantly increases the number of false positives, as there are lots of legitimate uses of these functions in models. We will explore that more later in the presentation. Now, let's move on to another model format, which is GGF, that was created by the JGML community. GGF is a binary model format that contains weights, architecture, and metadata. It is now supported by several open source popular libraries and runtimes. Most notably is Llama CPP, which is a CPP library and command line tool designed to run LLMs. Llama, which is a runtime and packaging system for managing LLMs locally. It works kind of like a package manager, allowing users to easily download, run, and manage GGF-based models. And Llama CPP Python, which is a Python wrapper around Llama CPP, providing a simple Python interface for loading and running GGF models. One key feature of the GGF format is its ability to store a chat template in the model's metadata under tokenizer chat template. This template defines how input and output messages should be formatted during chat interactions with the models, and it's written using Jinja 2. Jinja 2 is a Python template language that allows combining static text with dynamic content using variable placeholders, loops, and logic. Jinja 2 is powerful, but using it with untrusted input can be unsafe, potentially allowing execution of Python code. So when loading a GGF model from an untrusted source, a maliciously crafted Jinja 2 template can trigger arbitrary code execution. This vulnerability was disclosed as a server-side template injection SSTI issue, officially identified as DCVE and known as Llama Drama. This vulnerability affects only the Llama CPP Python library and was patched in version 0.2.72 Since Jinja 2 is Python-based, this vulnerability does not impact Llama CPP or Ollama, which don't use Python Jinja 2. Let's look at a real malicious GGF model that was uploaded to Hugging Face. This was a POC for the GGF SSTI vulnerability and was flagged as dangerous. In this example, the Jinja 2 tokenizer chat template includes a payload that runs a shell command that creates a file on the victim's machine. So to protect your environment against GGF threats, it's best to run GGF models in a sandboxed setup. To check whether a GGF model is malicious, you should parse the model metadata and extract the tokenizer chat template string and look for suspicious content like class, subclass, OS, subprocess, eval, exec, etc. Moving on to our last model threat, we will now explore TensorFlow and Keras. TensorFlow is another widely used Python ML library similar to PyTorch, and Keras is a popular Python ML framework providing a high-level API that is built on top of TensorFlow, integrated as tf.keras. Keras is designed to make building, training, and deploying deep learning models easier and more user-friendly. The thing with Keras is that it has built-in layers that each already performs a different model operation, and the user can just choose which one to use and how layers are connected. After training, it is possible to save a TensorFlow model in a few main formats. The first is the default called saved model, which is a directory that contains a complete TensorFlow program, including the architecture, trained weights, and computation graph. Then there is HD5, a legacy single-file format originally used by Keras and later adopted by TensorFlow. It stores both the model architecture and weights, and optionally the optimizer state. And lastly, Keras, which is a newer single-file format introduced in Keras 3. It is a recommended replacement for H5 and is designed to be more robust, version-aware, and forward-compatible. Like H5, it stores both the model architecture and weights and is also fully supported by both Keras and TensorFlow. These model formats become potentially dangerous when lambda layers are involved. A lambda layer is a feature in Keras that allows users to extend the built-in layer capabilities by writing inline Python functions that performs costume tensor operations, especially when those operations are not already available in Keras' built-in layer set. During the save and load process, the Python code is serialized and deserialized. When inspecting the Keras Lambda implementation, it was found that it uses Python's Marshall dump and Marshall load during the serialization and deserialization process. Just like with the Pickle module, Marshall also comes with a big red warning about usage with untrusted sources. The reason is the same as with Pickle. Lambda layers can be utilized to execute arbitrary malicious code. Here you can see an example of a lambda layer that contains compiled Python code. Malicious actors can use these lambda layers by creating a model with embedded harmful Python code inside the lambda layer. Once loaded by a victim user, that code will be executed on their machine. To identify malicious TensorFlow models, you first need to locate the lambda layer, then extract the raw Python code. Here is a short Python script that does that for the saved model format. It opens the Keras metadata file for reading and looks for a lambda class in the tf-keras layer node. Then you need to decompile the raw Python code. You can use the PyCDC, for example, and examine the code to identify any malicious instructions. Here's a real-world malicious model example of a TensorFlow saved model that uses lambda layers to execute code. After extracting the lambda Python code, our team found that it calls exec to dynamically import models and opens an HTTPS connection to protectai.com. It is important to note that there are more model threats out there that I won't be able to cover today due to time limitations. However, you're more than welcome to stay updated through our website, where we actually research and monitor new model threats and publish our findings. You can just scan the QR code on the screen. There you'll find the most up-to-date model threats with detailed information about each one, including the risk level, affected model formats, and real-world examples discovered on Hugging Face. The page also includes guidance on spotting malicious payloads and tips for reducing false positives. Now, moving on to our next section of this webinar, which is protections and how to bypass them. So, the battle between attackers and defenders is nothing new. Once attackers started targeting ML models, defenders had to respond. And one way they did that was by adding protections directly to the ML Python libraries. Let's take an example from protections embedded in TensorFlow and Keras, which we just explored. As you may remember, models with lambda layers can be dangerous, leading to code execution. To address this, Keras introduced a parameter called safe mode in version 2.13, which is enabled by default and blocks deserialization of lambda layers, preventing the code execution that could happen when the model loads. In this code snippet, you can see how it works. Whenever deserialization is triggered, safe mode checks if the class name is lambda, and if it is, it raises an exception. But as we often see, protections can be bypassed, and our research team discovered a zero-day that successfully bypassed this protection. The key insight is that safe mode protects against lambda layers with underscores in their class name, but it doesn't block another type of Keras lambda layer that you can see here. Not surprisingly, that variant also allows code execution during deserialization. This new POC works differently from the original POC of lambda code execution. Instead of using marshaled Python bytecode, it relies on 3 keys in how lambda is configured. Each lambda configuration contains arguments, function, and inbound nodes. Here's what happens in the lambda layer calling process. The function lambda layer call executes the function defined in the function field and passes a tensor object created from inbound nodes as the first parameter, and finally supplies named arguments from the arguments field to the called function. To exploit this mechanism, attackers need to find a Python function that ignores the first argument, accepts additional named arguments, and performs a useful operation for the attacker, like running a shell command. In Keras vulnerable versions, any Python function from an importable module can be referenced. The most useful function we found for this exploit is n-smallest from Python's standard heapq model, which takes 3 arguments: n, iterable, and function. N is the first one, and since it does not enforce a specific type for its first argument, it perfectly matches the requirement for successful exploitation. The iterable contains a list of arguments to be passed into the function, and the key argument is a central component that executes an arbitrary function on each element of the iterable. This function can be any call to execute code, such as exec, eval, OS system, or subprocess bopen. When we put it all together, it looks like this. The class name is lambda. The heapq n-smallest function is executed, pulling its arguments from the arguments field. That field contained the key, which is the Python function to execute, OS in this case, and a iterable which contains the arguments, ls-l in this case, that results in executing it on the victim's machine while safe mode is enabled and set to true. This exploit is only relevant for versions lower than 3.9 because it allows all Python functions to be referenced. However, version 3.9 fixed this issue by limiting the loading of functions to be from Keras models only, which is a good start. To bypass that, we used other dangerous functions that the Keras model itself contains, which is the Keras utils getFile function. This function is designed to download files from a specific URL, and if instructed to extract them, can be exploited for arbitrary code execution. Using this exploit, an attacker is able to download a file to the temp directory of the victim's user, again when safe mode is enabled. Another interesting exploit option to get full SSH access to the victim machine can be downloading a malicious authorized key file into the user's SSH folder. Moving on to another protection method, let's explore Hugging Face scanning methods. To help defend against these model threats, Hugging Face introduced several measures, including malware scanning, pickle scanning, and secret scanning. These tools inspect every repository file for malicious code, unsafe deserialization, or sensitive data, and alert accordingly. Relevant to our discussion is model scanning, which is used to determine whether a model might be malicious. Here you can see an example from Hugging Face where a model is flagged as malicious. Notably, models identified as malicious are not removed from the platform and can still be downloaded and executed by unsuspecting users. JFrog and Hugging Face join forces to integrate model security insights provided by JFrog scanners in the Hugging Face platform, allowing users to inspect the model security before using them. Let's take a closer look at what we actually do and the support systems that make our scanners more accurate. The JFrog Security Research team has developed a scanning environment that carefully examines every new model uploaded to Hugging Face to detect and alert emerging threats. Right now, our X-ray database holds about 340 malicious models. Each one has been carefully examined by our team, covering the different model threats we've talked about and more, including PyTorch, Pickle, H5, SafeModel, Keras, NumPy, JobLib, Deal, and Paddle. Our scanners detect code execution during the model loading process and analyze that executed code in detail to decide whether it's truly malicious or completely legitimate. You'll see more about how this works later in the presentation. We also have a dedicated research team that manually verifies malicious models caught by our scanners. And this team also monitors newly published malicious models as well as new threats, such vulnerabilities in that landscape. This way, we can quickly spot fresh threats and update our scanners to stay ahead of the game. What really makes our scanners powerful is the multi-layered verification process. It ensures accurate detection of malicious models, minimizes false positives and false negatives, and continuously improves our scanning algorithms. While other malicious model scanners exist in Hugging Face, we notified significant accuracy issues, both false positives and false negatives. Let's start with the false positives. We have found that the current model scanning solutions we tested are pretty naive. They mark your model as malicious if it runs any startup code or uses any blacklisted Python function or includes any use of GateATR or any calcium layer. While this sounds reasonable, these rules break down fast in the real world because many models legitimately use startup code when they loaded or use blacklisted Python functions, calcium layers, and GateATR. Some of these are very common, and flagging all of them as threats significantly increase false positives. It wastes security teams' time. Let's look at an example of a model flagged as suspicious and unsafe by some scanners on Hugging Face. This model is a test pickle model that even states it should not be considered as malicious, yet it still triggers alerts simply because it is pickle-based. Interestingly, one tool flagged this model as malicious, but also states it's not yet scanned. While JFrog scanned it and found no clear indication of malicious behavior or any harmful activity. The only notable element was the use of getATR, which, as we've discussed, can be abused for malicious purposes, but in this case contains nothing dangerous. Unfortunately, legitimate uses of getATR can still confuse detections and lead to false positives, which is most likely what happened here. Another false positive example is the TensorFlow Keras saved model officially published by Google, which wouldn't raise any red flags since Google is a trusted vendor. Surprisingly, one tool flagged this model as malicious, but again, hasn't scanned it yet. And again, our analysis at JFrog found no indication of malicious activity. To avoid these false positive cases, we carefully research each model threat and develop targeted detection methods. While startup code, blacklisted Python functions, custom layers, and getATR raise red flags, it's not enough to mark a model as malicious based on that alone. JFrog digs deeper to determine if the code is truly dangerous or just normal model behavior. For example, startup code may set legit environment variables, which is harmless, or run dangerous commands like OS system executing a destructive shell. Blacklisted functions such as TensorFlow read file can be used legitimately to read model files or maliciously to access sensitive files like etc passwd. Lambda layers aren't always dangerous. They can do simple math operations or be used maliciously to run system commands. And getATR is mostly used legitimately to dynamically access methods like those in math model, but can also be abused to open shells and execute code. The getATR alone caused 4,000 plus false positives to other scanners in Hugging Face. As we saw with the previous example, today ML model scanners don't consider context and treat all possibly malicious functions the same, which causes many false positives. By combining multiple checks, JFrog can distinguish safe models from truly malicious ones, reducing false positives while catching real threats. So it all comes down to context, just like any other security issue. It is a key to reduce false positives and improving detection accuracy. Looking at the numbers, other scanners on Hugging Face flag over 8,000 models as malicious, while JFrog flags only around 340. This means more than 7,500 models, about 95.75% are false positives. When examining these false positives, we found the main reason is what we just said. These scanners don't consider context and mark all possibly malicious functions as malicious, even when they're called with legitimate arguments. If these other scanners already generate thousands of false positives for well-known and obvious threats, then when they attempt to detect newer, more subtle techniques where detections is inherently more challenging, the numbers of false positives will explode. This makes their findings harder to verify and slow down research and response. JFrog takes a different approach thanks to our advanced tooling. Our results are provided with evidences for researchers to validate potential threats. We can run deeper verification checks, and we can seamlessly integrate these capabilities into our products. We apply noise cancellation to focus only on truly suspicious activity. As a result, even when we hunt for unknown or emerging threats, our detection remains precise and actionable. In case you thought that was the end of it, unfortunately, it is not. We found it even more concerning when we identified 25 models flagged as malicious by our scanners, where none of them were also classified by other Hugging Face scanners. One key reason is that in some frameworks, models can transitively import other models. While these can be legitimate, for example, combining multiple pre-trained components into a single workflow. It can also be abused as an obfuscation technique for malicious code. An attacker might publish a seamlessly harmless model that, when loaded, silently pulls in another model containing the actual malicious payload, which hides the true threat from scanners that only inspect the outer model. For example, suppose model A appears safe with no malicious code found inside it. However, when we examine it closely, we discover that it imports model B. Model B is found to be malicious. Then model A should also be considered dangerous, and not marking it lead to false negatives. Our approach goes deeper by analyzing these imports end-to-end, following potential long chains of dependencies, often more than just one or two hops, to inspect every reference model, ensuring malicious behavior hidden behind such interaction is detected. So, where does this leave us? Right now, when we look at model-based attacks in public repositories, the reality is they're still quite immature. There aren't a huge number of malicious models out there. If you remember, JFrog X-ray database contains around 340 malicious models out of 1.8 million models hosted in Hugging Face. And the ones we do see often have very simple payloads. In fact, most of them aren't even truly malicious. They're more proof of concept than an actual real-world threats. But there are some real threats out there, and if those aren't identified in time, they can cause serious damage to organizations. Now, even though not all malicious models are truly dangerous, the fact is it's an extremely easy to target for attackers. Anyone with basic skills can build a malicious model using public tools in just minutes. That's why it's so important to stay ahead. Platforms like Hugging Face, hosting massive number of models, become prime real estate for attackers to plant their malicious assets. Since we also saw that Hugging Face doesn't actually remove models flagged as malicious, it becomes even more critical to have strong scanners that can correctly and reliably identify them. The problem we've already explored today is that some scanners just aren't accurate. They generate a flood of false positives and false negatives, and even the mitigations provided by ML libraries are not bulletproof and prone to bypass techniques. This not only hurts trust, but it wastes valuable time for security teams and slows down adoption of these models. So, should you trust JFrog? If you stayed with us through this whole webinar, you've seen for yourself that JFrog actively monitors and scans new malicious models while providing unique and accurate security analysis for them. It is important to mention that our scanners are not only available through the Hugging Face platform, but JFrog also provides security scanning and real-time protection with JFrog X-ray and JFrog Curation products, which enables you to block malicious models before entering your code and putting your organization at risk. Thank you so much for listening. We will now have a live Q&A session with Shachar Menashe. Terry, back to you.
Orphy, thank you so much. We always welcome this sort of original research. It's a great barometer of where we are with ML vulnerabilities. Thanks for a really timely presentation. Onto a presentation, or the Q&A portion of our event day. As a reminder to our audience, just type your question into that text box located to the left of the presentation window, or click on that Q&A icon at the bottom of the screen. If we're not able to get to all your questions, we'll be sharing them with both Orphy and Shahar, as she mentioned, who will be handling the questions today. So Shahar, welcome so much for stepping in here and dealing with some of the questions that have come up. It's good to see you.
Thank you.
Let's start with a question from Todd. Orphy took a bit of a stab at this in the presentation that we just heard, but Todd is asking, how many false positives have you seen while finding 360 malicious models? Given that, how does JFrog guarantee no false negatives? Shahar,
Yeah.
can you take a deeper cut at that?
Yeah, for sure. Yeah, so we covered it a bit in the presentation. It was after the question was asked, so that makes sense. But still, I'll take a stab at this. So we've seen a lot of false positives. It was like we said in the presentation, it was 7,500 false positives when we were going over the entirety of Hugging Face. Like we said, we went over 1.5 million, so 360 true positives and 7,500 false. By the way, the false positives are still there; they're visible. So if you would run around, you will be able to see some models that are marked as let's say malicious by one scanner and let's say non-malicious by JFrog scanners. And the reason for the false positive we also elaborated on a bit, which is some scanners are just looking at the surface layer, like saying, hey, if the model is trying to run any code whatsoever, then it's malicious. And a lot of libraries like FastML that you use to build models, they will inject code, which is, of course, completely safe. And then, some scanners might say it's malicious while it's not. Regarding the part about how we guarantee no false negatives, so we take a few approaches. So first of all, when we scan for malicious models and malicious packages, we have a score-based model. So that means that if the package ticks some boxes or the model ticks some boxes, and a lot of the boxes that we check for, then it would have a very high maliciousness score. So if it has a very high maliciousness score, we say, okay, it's for sure malicious, and we add it to our database. But if the score is somewhat medium, that means it looked like it did some things that look suspicious, but not something definitive. Then it gets sent to our research team for review. So that way we can both automatically, make sure the things that look extremely malicious are passed on to the database. But if there's something that we're not sure about, we can still keep our scanners somewhat lax. Like they're not super strict, they're a bit lax. And then if we get a medium score, then we look at it ourselves. So that way we can also catch the very obvious things, but also something that's not very obvious and avoid the false negative. So that's one. Also, is sort of, the proof is in the pudding. We are seeing that we're just finding ML models that nobody else is alerting on. So that's obviously a proof that, okay, so at least we're seeing things that others aren't, so that's not false negatives from our side. So that's also something that we're seeing. And of course, we're also always looking at other publications. Like if someone else said they found a model, then, when we started out, yeah, it might have been a model that we didn't actually find. So we saw, what is this model? Why didn't we find it? And then adjusted our scanners so that we'll find it. So it's a constant feedback loop to make sure we find everything. Yeah.
Thank you for that. Todd from our audience is also asking, how would you recommend using a VM to extract models in order to detect malicious code execution during the load? You have some thoughts there, Shahar?
Yeah, for sure. So we actually have a good resource for that. So first of all, if you want to extract the interesting or like extract the code from the model, which again is usually where the malicious stuff is, then I actually don't think a VM would be the best solution, because like you would use a VM if you would use a VM to load the model, then you can do some runtime analysis on it. Like the model will run and then the payload will run, unless it has VM checks. The payload will run, and then you can catch the malicious payload, with the usual tools like If it's Windows-based, then procmon and things like that to see what files it writes to, registry, network, etc. But if you want to extract the malicious code from the model, then I don't think a VM is a solution. So luckily, I also sent in the answers, we have a good resource for that. So in research.jfrog.com/model threat, and I wrote it also in the answer, for each type of attack, we actually say how we perform the extraction. And it's based on open source tools. Of course, we have our own logic afterwards how to determine it if it's malicious. But only to perform the extraction, it's mostly based on open source tools. So for example, for pickle-based, there's a great tool by Trail of Bits that's called Fickling that can do the extraction. For H5 Lambda layers, there's the H5PY library that you can use. Like you use it to get like the extracted code as base64, and then you need to decompile it, like Ofri mentioned with PyCDC. But we have these steps in the model threats resource page, so you can just look there, and we say exactly how we extract it.
Good stuff.
And yeah, and when just to clarify, when you extract it like that, you don't need a VM because you're not loading the model. You're doing everything statically, so there's no risk of the code running, the malicious code running.
Okay. Shahar, Jonathan from our audience asks, 340 plus malicious models on the entire Hugging Face repository seems small. Does that mean this isn't a huge problem yet?
Yeah, I think also we did mention it also in the slides. I agree with that for now. There's 1.5 million models. Not all of them also, well, now there's even a bit more, maybe 1.6. Not all of them are in a format that can allow for malicious code execution, but actually the majority still is. I think 60% is pickle-based. So the majority is still in a dangerous format. And only 300, like now we found 360, a bit more, maybe 400 since it was last updated. But still, 400 out of 1.5 million, yes, it's small. We are afraid that this will become a larger attack vector as time goes on. Because like we said, a year ago, it was, there was 3 times less models, but 7 times less malicious attacks. So the amount of malicious attacks jumped more than the amount of models. The amount of malicious models jumped more than the amount of non-malicious models. So right now it's small, yes, but we believe that it could get larger and larger, and only just one is enough to hack into an organization. So that's why we're very vigilant on that.
All right. Another audience question from Abhijat. Are there any web services, REST services offered by JFrog that we can integrate in our pipeline, including signatures, et cetera, so that it's already invoked?
Yeah. With JFrog, we offer all our services both as managed, like SaaS, and self-hosted. So SaaS would, obviously be like the web services, REST services, and we have 2 products that can handle the malicious models. The first is curation, where basically every Hugging Face model, for example, that you pull into your organization, you pull it through Artifactory, and then if it's malicious, it just won't get pulled. So that's like a preemptive solution. And we also have X-Ray that whatever is stored in Artifactory, it can identify models. And again, if it's malicious, then it will alert, and you can set policies to do whatever you want with that, like block the download or create a JIRA ticket or whatever you want. Since we have cloud version, like a managed version, then of course all this data is available through REST API and whatever, like it can be used through automation. We have various means of automating it, like a CLI, REST API, even some like GitHub specific automations because we have a partnership with them. So yeah.
All right, we have time for one more question. Todd from our audience, who's on fire here. Great question though. He's asking, it seems that JFrog is focusing only on malicious code execution. What about threats hidden in the model itself? There have been several methods for this in the research. Shahar, can you do that real briefly, please?
Yeah, I'll keep it short.
As best you can.
Yeah, I'll keep it very short. So, great question. This is something we started from malicious code execution because it's the easiest to exploit, and we saw people actually exploiting it right away. The threats in the model, like architectural backdoors in ONNX and things like that, like putting backdoors in the model that will make the model spit out unwanted output. This is what we're researching right now, and we expect to be able to detect those attacks as well. It's not the MVP attack, so we didn't start there, but we're doing it now.
Excellent. Well, that in fact is going to bring us to time. I want to thank both Ofri Uzan. We appreciate your time and expertise on today's topic. Also, big thanks to Shahar Minash for answering questions during a Q&A. Great job, Shahar.
Thank you for having me.
Thank you as well to our sponsor, JFrog, as well as everyone in the audience. Y'all never fail to disappoint with the great questions. So thanks very much for the attention and participation. Sometime in the next 24 hours, you'll be receiving a follow-up email with details and a link to today's presentation on demand. Please feel free to share this with colleagues and peers who couldn't have been part of today's live event. Now for the boilerplate, this webinar is copyright 2025 by Informatech Target. Presentation materials are owned by or copyrighted by Black Hat and JFrog, and individual speakers are solely responsible for their content and opinions. Okay, on behalf of our guests, JFrog and the Black Hat team, I'm Terry Sweeney. Thanks so much for joining us for this installation in the Black Hat webinar series. We'll see you next time.